I have the other stream up on my screen just to see where we're at.
Okay. Great. Sorry, I'm trying to get the company's logo in there, but not my messiness of the office. Oh, well.
Hi, everyone, and welcome back for our last talk of the day. We're very, very lucky to have Dr. Matanya Horowitz as our speaker. Dr. Horowitz is the founder and CEO of AMP Robotics, an industrial AI and robotics company that applies automation to modernize recycling and enable a world without waste. Fast Company recognized Matanya as one of 2020's most creative people in business. Waste 360 named him as the 2019 Innovator of the Year and included him on its annual 40 Under 40 list. So welcome, Dr. Horowitz. We're really happy to have you here.
Thank you very much. Really glad to be here. I'm always excited to talk. This is my bad joke. Always excited to talk trash. So,
you want to share your screen?
Yeah, excited to get started here. Let's see. Oh, I'm sorry. Just made a small mistake. So yeah, very excited to share a little bit about what we're doing here at AMP Robotics, where we are using artificial intelligence to help transform the recycling industry. So for those of you who may not be familiar with recycling or waste, a tremendous amount of value is lost to landfills or incinerators each year. If you look at the total volume of what could be recovered, whether it's in plastics, metals, papers, what you're seeing is, over 80%, over 90% of this material is largely being thrown away instead of recovered. The interesting thing is that if you total up the value of all of these different material streams, you actually find that there's a great deal of value there. And these end up being numbers like 200 billion, sometimes even looking at around $300 billion. I think a lot of people have the impression that recycling is done as something to make you feel good. Maybe it's politically motivated, but in fact, actually, these materials do have a tremendous amount of value. So the question is if this stuff is so valuable, why isn't the recycling industry a larger fraction of the waste stream? And the answer is that the state of technology today means that the cost of extraction for these materials rivals the innate value. So if you look at a ton of material coming out of a residential community, it might be worth $80 per ton or $100 per ton. And you find the cost of running a recycling facility or somehow processing that material, it can be $60, $80, or even $120 per ton. So the economics can be challenging, and that's why not a lot of this material is recovered. But at AMP, what we are doing is improving the fundamental economics of the recycling process and creating a stronger incentive to divert this material and reuse it. And some of the central tools we use are robotics and artificial intelligence. We really think that these technologies open up new doors in how we deal with all of this different material. So a little bit about us. We have hundreds of robots and vision systems all around the world, mostly here in the United States, but we've recently expanded into Western Europe. We have some systems over in Japan. We have happy customers, customers that have bought dozens of different systems. These include the main haulers in the country, so groups like GFL, Waste Connections, smaller entities that may only have a single recycling facility or two, groups like RDS. And we have some fantastic investors that are excited about what we're doing with recycling. So groups like Sequoia, Congruent, XN, Google Ventures, Sidewalk Infrastructure, and Closed Loop, who with us see the potential of this technology being used in the recycling industry. So to give you a little bit more detail about the recycling industry right now, a lot of it surrounds these recycling facilities. They're called material recovery facilities in the industry lingo. So when you bring material to your recycling bin, or you put material in a recycling bin and that's left at the curb, that's brought by the hauling truck over to a recycling facility and largely dropped off. What you'll see in these places are lots of conveyor belts, a lot of machinery that you might see in mining or in agriculture. So different things like trommels, different types of screens that are trying to separate out the material coarsely. The systems don't work that well, and so you see a tremendous amount of manual labor being used to fix the mistakes that other equipment makes. So the cost of sorting is high. A lot of this equipment is not very robust to the material it's processing. You need a lot of manual labor in there. Lots of mistakes are made. So sorting costs are high. There's all sorts of contaminants. People put in diapers, hypodermic needles, propane canisters in the material stream. And this gums up a lot of the equipment. Plastic bags is a different one. Also, the material itself, even though it's recyclable, if it changes, it can find its way into new corners of the recycling facility and create issues. So one common problem recycling facilities had is that when people started to buy more material at home, more things at home, basically cardboard boxes started to get smaller. And now the cardboard moved differently inside these recycling facilities than they've been designed for. The sorting tasks that these facilities have are fairly unpleasant. You can imagine there's rotting food, there's these hazards. And so all of the, pretty much every recycling facility you might visit, they're running understaffed, they're dealing with high turnover, and it makes it even more challenging to extract the full value out of these pieces of material. So coming to the rescue is artificial intelligence. What we think is that artificial intelligence solves some of the main challenges in the recycling industry and enables new capabilities that really hadn't been possible until now. And so we'll get into that. So what these systems look like, here's one of the robots we have deployed. It is happily sorting out two plastic resins, natural HDPE and colored HDPE, so milk jugs basically. We are deploying these robots with almost no retrofit into recycling facilities all around the world. What you see here is this frame that's been bolted onto a conveyor belt they already had on a material stream that looks exactly the same as before we got there. So they don't have to change their recycling facility for our tech. The robot is actually a sort of off-the-shelf robot already commonly used in the manufacturing industry. The magic here is the vision system that we've built on deep learning that lets us identify all of these different commodity types. We can identify all the different resins of plastic, different types of platinum, different types of metal, different types of paper, and so much more. What this technology can do can actually not only match, but beat the quality standards that the industry has today. So getting effectively 100% purity on the different materials that we're sorting out, which is quite difficult to do either with the technology that exists or outside of AI or with the manual sorting. And the way we like to look at it is recycling has gone through two previous stages of innovation. So the first, the recycling, if you go back 50 years or more, was really about people standing around picking stuff by hand. There was then a shift where mining and agricultural technology started to be used. And this is really different types of mechanical separation using some sort of physical property of the material, like density, surface area, other things, to sort of coarsely get all different commodities in different spots. And that sort of worked well. You were able to get better leverage over your manual labor. In the 90s, there was then a shift towards the use of hyperspectral technology. So this was infrared sensors, ultraviolet sensors, X-ray sensors, all sorts of things, where different plastic resins, different types of paper would have a very clear spectral response. And you could then use that information to separate specific commodity types. Now, artificial intelligence, we think, is at the beginning of a new wave for the recycling industry, where you have a vision system that can learn to identify pretty much anything a person can be taught to identify. Any such sensor we deploy can identify all the material streams. So even though we have a robot picking aluminum cans in one corner of the world, it's still seeing all of the milk jugs and all of the office paper and other things like that. And it's seeing it at a very high accuracy that's quite robust to say how dirty it is, or if it's filled with a liquid, or what kind of labels are put on it. All of these things are sort of contaminants or create challenges for the existing equipment. Just to give you a little bit more sense of what this looks like, yes, you can use an example like cardboard, where you're looking at the sort of the stiffness, how flat it is, how two-dimensional it is versus how three-dimensional it is. You're putting it over some sort of screen, and that screen isn't going to be intelligent really in any way. It's just going to spin some sort of disk or spin some sort of sorting mechanism to agitate the material. And because of these physical properties, different types of material move to the right spots in these facilities. That works. You can get coarse separation at very high throughputs, but it's all very low purity. So a lot of this machinery will produce material that's, say, 70 or 80% pure. And then you have to go the rest of the way to kind of a 95% target using manual sorting. So as an example, what you have over here is a paper screen being shown on the right in green. Roughly 15% of the material that goes over that will be cardboard and other stuff you don't want with the paper. And people will largely pick that out. With AI, what you're doing is you are looking at every individual piece of material in real time. You're able to say, that's a piece of cardboard, it's sitting on a piece of paper. I have sort of total situational awareness about what's going on. And then you can have a mechanical device that will then intelligently go after the material you care about. And what's powerful about this, well, a number of things, but one of it is if you're identifying all of the material, you can design sorting equipment like robots that are generic across all material types. It's happy to pick an aluminum can. It's happy to pick a piece of cardboard. And this gives you a lot of flexibility in these facilities. So, as to what this looks like at a full installation, well, on the left, we have a single robot by itself. You see a conveyor belt with a vision system ahead of the robot. There's an electrical cabinet where our compute sits. But then you have this enclosure for the robot. These robots are called Delta robots. They're some of the highest speed robots that are available. And they're reaching into the material stream, pulling stuff out. This is at one of our customers, single stream recyclers in Sarasota, Florida, where you have robots doing all sorts of different things. We're cleaning up the paper. So this is the paper that comes from one of those screens. We're cleaning up the different resins of plastic and such. For a typical recycling facility, we can automate 3/4 of the different sorting stations. And that's roughly what we've done here. I think for SSR, our single stream recyclers, we did roughly 2/3. But yeah, we have the sensing compute on the front end. We identify the material. We sense the belt speed with a couple different mechanisms, and we say, okay, robot, there's a piece of material over here, and it's coming at you, and it'll be there in 1 second. And then we tell the robot what to go in and pick. It's very easily reprogrammable. The robot's identifying all the material. So if you want to have it pick paper one day or aluminum cans the next day, it's happy to do it. And the way it does it is with this vacuum gripper. So you can see there's a hose that conveys this vacuum over to an endpoint. We've had tremendous success with pneumatics and suction as a grasping mechanism. A lot of people think you might want to use a mechanical grasper. You absolutely could. It actually ends up being really difficult because the material is inconsistent. It's also all piled together, so you're going to have different non-target items right next to the thing you're going after. Some of them will be overlapping, and it just creates a number of different challenges that we've been able to overcome with suction. And here's one of these up close as to what the sort of gripper and everything looks like. This is in our lab here in Colorado where we're picking, this is natural HDPE, but milk jugs. I guess a couple pieces of colored HDPE if you're in the know. And robot's happy to do this all day, every day. I think our longest lived robot so far is about 5 years old, but it is still going strong. Within these facilities, there's a number of different niches you can fill. So one of these is what's called quality control. So in this case, you're not actually trying to pick all of the material. There is some material stream that you want, and you're pulling out the contaminants. It's a pretty tedious job. If you're doing it manually, so you're standing looking at this material, and you have to catch all the paper bags. What you find is even if you're trying to do a good job, after a couple hours of doing this, it's really hard not to zone out and miss material, even if it's right there in front of you. The consistency of the technology in these applications is alone a huge benefit for these recycling facilities. One of the other applications is what's called the residual line in these facilities. It's essentially the last location in the facility where all of their yield losses go. So throughout the facility, they're pulling out different types of contaminants. They're pulling out different mistakes that the other equipment's made. And all of this stuff will go to the landfill. Our robots can be put on those lines, and they recover all the material that still has value to recirculate into the system. And so, yeah, there we're actually picking just about everything, and we're leaving the true garbage behind, which will then go to the landfill. Very common use case for these systems. In both cases, the robots work at 80 to 100 picks per minute. This ends up being about double what a person can do. So a person actually can get up to 80 picks a minute, but not reliably and not consistently. If you find yourself kind of sorting at that pace, you'll get tired after half an hour or an hour. You'll drop down to something more like 30 or 40 picks per minute, and that's what is considered an industry average. So at 80 picks per minute, has huge leverage for these facilities, and in particular, the ability to put a robot in a spot where a person is and potentially have double the throughput can increase the performance of the facility as a whole. As to the vision system, so our vision system sits in front of all of these robots doing the real identification. This is really the innovation we've had. The robot is off the shelf. It's been around for decades. The pneumatics, we've done some pretty clever stuff with it, but to kind of specialize it for this application, but there wasn't anything that really kept people from doing those things before. What had kept this from happening, 10 or 20 years ago was a lack of the ability to identify all of these commodities. So our vision system does that, and really what it's doing is deep learning based inference. It's edge compute, so we have essentially a high-end gaming machine that's identifying this material. And that can be used for a number of different tasks. One is with our robot, but we also use it just purely to identify material and provide business intelligence to these facilities. So we can tell them how pure a material stream is. We can tell them if their other equipment is breaking down and there's a lack of material or an overpresence of other material in a specific spot. All of this information they don't have a way of getting currently. The best you could do is actually have someone running around with a clipboard counting stuff by hand. If you can't measure what's going on in a facility, it's really hard to improve your operations. And so as a result, you've seen that a lot of the industry is really governed by sort of rules of thumb, different best practices people have established, different hunches about what's going to improve operations. But with a sensor, you have a real means of making that become a more scientific process. So as an example, we can go back to this screen and we can do things like put a vision system in front of it and behind it. We can tell you when things are going well, when things are not going well, the efficacy of that machinery. If you want to try some sort of experiment, you can now really measure that. And you can do it continuously with pretty much no intervention in your process. All of this is pretty much impossible currently in the industry. And this just gets into a little bit more of an example of the detail of why you would need to do this measurement of the purity of these different material streams. So these recycling facilities are separating out, depending on the facility, 8 to 12 different commodity types. These will be things like cardboard, number 1 plastics, number 2 plastics, office paper, newspaper, things like this. For any of these, there's a standard associated with it. So for certain plastics, you really want to be 98% pure. For a lot of paper, it might be 95% pure. And the things that you consider contaminants will be different material stream to material stream. So in your plastics, paper is considered a contaminant. In your paper, plastics are contaminant. Everywhere, diapers are a contaminant. Of course, but so for each different material stream, you have to be able to identify pretty much all the different material types and know what the correspondence is between allowed and non-allowed materials. With our vision system, we identify it at a much higher resolution. So we're saying, okay, this is a number 1 plastic, a number 2 plastic. We may even have information about the brand of that material, whether it has labels on it or not, and things like this. And we use that information to look at the overall purity of these different material streams. We built this into a business intelligence platform that we call Clarity, where you can have different insights around the whole recycling facility. So you can measure what's happening on the input of your material stream or of your facility, anywhere in the middle, anywhere at the output, and get a really cohesive view. We think that these capabilities are going to help bring best practices that are already common in manufacturing, oil and gas refining, agriculture, other places, bring all of these different ways of running a factory to the recycling facility and make them more efficient. Without sensing, it's really hard to adapt best practices from, let's say, lean manufacturing or other things, but now it becomes possible. We've then also gone one step further. So our focus had been on the design of these very specific pieces of equipment. So the robots, the vision systems, into the design of an entire recycling facility. And what we are doing is actually taking material from other recycling facilities that are either very low value or otherwise going to the landfill and reprocessing them to either increase the purity or recover more material. So what you have on the left is sort of the beginning of the recycling industry. So stuff coming out of collection trucks. That goes into a recycling facility that is then trying to pull out these different commodities. What you find is the efficiency of those facilities is around 70 to 90%. So out of 100 plastic bottles that go in, 70 to 90 will actually be captured. Some will go to the landfill as a yield loss. It's for a number of different reasons. The equipment's not perfect. It may have a contaminant on it or something else. That other material will be called residue, and that'll be landfilled out as yield losses. What we are doing with artificial intelligence is creating a new type of facility that actually accepts the stuff going to the landfill and pulls out some the remaining fraction of high value materials. The reason this is possible and hasn't really worked out before is that artificial intelligence allows you to measure and control that material stream in a much better way than what you'd been able to do in the past. So you're able to extract that material at a much lower cost. Everybody in the industry already knows there is value in the residue, but what happens is it's effectively diluted with more garbage. And so is it profitable to sort out? If your cost of sortation goes down, now it can be profitable to sort it. And that's what we've enabled here. What's fun about this is that we are applying this to what I might call an old world or old school industry, but there's a lot of analogies to other technologies that are being developed, whether it's autonomous cars or other things around machine learning. Where when we are deploying our technology, we have a strong focus on the idea that machine learning technology and robotics technology is moving quickly. Its performance is largely governed by software. And so for something that's deployed today, it's going to get significantly better over the next year, over the next 5 years. And so we've adapted our business model around this. For all the systems that we deploy, there's a strong focus on software updates and adding new functionality to that existing hardware. And yeah, I think it's very similar to what we've seen from groups like Tesla and others around that use machine learning as a core facet of what they're doing. I think everybody readily knows that the technology of today is not as good as it's going to be. And so you want to adapt, you want to future-proof your products. And that's absolutely possible with what we're doing in recycling. To get a little bit more specific, I'm going to talk a bit about our vision system, Neuron. So Neuron is the name we give for basically our data platform. This is the vision system that's common in our standalone vision product, in the robot, and any other sorting equipment that we build. So what we have is a actual vision device, basically a color camera connected to a high-end gaming machine that sits on the premises and does edge inference. All of those systems are networked together to the cloud infrastructure we've built. So we're able to gather data from all of these different sites, correct mistakes, try out new neural network architectures, make improvements, and deploy those updates out to the whole fleet. So we have systems that have been out there 5 years now who are still getting updates from new systems that are coming online in Japan or Europe. We have a strong thesis around the use of color cameras. There are other technologies that help make this problem easier. So the hyperspectral systems that I mentioned earlier, using infrared or ultraviolet, or even X-ray. But our thesis has been that if this material is distinguishable by people, then a color camera should be sufficient. And almost all of these materials are separated by hand today. This is important because we want consistency across our sensor base. We also want to use the low-cost color cameras. Infrared technology and other hyperspectral systems are quite a bit more expensive. Yeah, we've integrated this with high-end graphics cards. We use a great deal of NVIDIA GPUs to do the inference. And it is important that we're identifying this material in real time. 10 milliseconds, 5 milliseconds, or 50 milliseconds will make the difference between having a good pick or a bad pick. And so you do have these real-time requirements. And then these recycling facilities absolutely can't shut down if they lose internet access or anything like that. And so, so beyond just the latency, high reliability and uptime is key. And so that also pushes you towards identifying the material on the edge. This is an example of what the real world looks like for us. So this is a real recycling facility. This is how materials presented to us. So items are commingled. Something to pay attention to is every piece of material is different in some way. It is smashed, folded, or dirty. The orientation is inconsistent. It is, not just deformed, but ripped apart. And you need to be able to identify it regardless. We're identifying dozens of different categories here. So cardboard, paper magazines, aluminum cans, other forms of metals. And you need to be doing this multiple times per second. These conveyor belts will run up typically at belt speeds of 200 feet a minute, but they can go up to 600 or 800 feet a minute, which is pretty fast. That's sort of like a sprinting speed. And so you only have, a couple observations of the material. And this creates a very interesting machine learning problem. So you're able to capture a lot of data, but you have a higher degree of deformations than I think pretty much any other application I can think of, and occlusion is quite significant. So dozens of supported categories. Looks like I didn't get this video working right. Okay, but today we have different accuracies for different materials, but largely we have purities over, 97%. It can be a conservative number. We'd say in some cases over 99%. Recall rates over 90% on most material types. In some cases, it can be effectively perfect. And just depends on the specifics of the situation. The material types we go after aren't just single stream recycling. We also have electronic waste applications and construction and demolition applications. In that case, you're identifying pieces of PCB and different types of aluminum. You're also identifying wood, rebar, masonry, bricks, things like this. So a really wide variety of materials in these different streams. And that's the power the industry needs today, but we're going beyond that. We're identifying many of these materials at the packaging level, or I'm sorry, at the form factor level or the brand level. So being able to say things like, oh, this isn't just paper, this is a coffee cup. Oh, it's not just a coffee cup, but this is a Starbucks cup. This gives you incredible control over how you monitor and also control the material stream. What you can do is you can understand, based on the brand and the form factor of the material, all sorts of interesting physical properties about that piece of material. You can also do things like separate out a brand-specific material and return it back to that brand for reuse. But what this means is your neural networks aren't identifying dozens of categories, but hundreds of categories. And doing this while all these materials are heavily deformed. Some of the interesting things about our use of the technology in the recycling space are, well, there's a couple different things, but maybe some of the most interesting are that you do have deployment at very, very different scales, and you have very different behavior for these machine learning systems at those different scales. So when you have kind of just a handful of units, or just your first unit, you don't have a deep data set. What you find is there is incredible inconsistency in the performance of the system. Since every piece of material is coming in a different orientation, different smashed and folded in different ways, you find it very hard to bootstrap the data set. You end up wanting to do a lot of specialization. So your neural net is very specific to each system. You may even have neural nets for different lighting conditions, all sorts of things like this. Yeah, there were all sorts of funky situations where, aluminum cans might come in one orientation and it would do a great job, and then you rotate them 90 degrees and it does terrible. So really inconsistency, and for a product, especially an industrialized product, real confusion by customers who don't really get why, if the aluminum can is rotated a little bit, why it does or doesn't work. So you get a lot of frustration if you're not doing a good job of setting expectations early. When you start to get to 1 to 10 units, you're still specializing, at least what we found, for different scenarios you run into. Almost every scenario is different in some way. Almost every scenario cares about performance of a different piece of material. So you're still dealing with a lot of site-specific stuff. And especially as you get more units out there, it's harder and harder to support them because each one is its own little unique system. And the machine learning or the inference you need is, its own unique snowflake as well. But then beyond that, you start to see, after you have 10 sites, 20 sites, that there's a stronger degree of generalization. So your neural net is able to do well. You have higher leverage from each site as it contributes to the whole. And by then, at least for us, we were able to really start specializing different neural network architectures and different technologies for the recycling industry and start to gain, very high levels of performance. As to why this is, I touched on a little bit earlier, but if you compare this against autonomous cars, as one of the main examples of machine learning, it's in many ways much more challenging. You have such a high degree of deformation on the materials that to a lot of these systems, they appear as entirely different objects. There's no consistency like two headlights and the headlights and windshield position always being relatively the same. The top of the aluminum can could be, in any orientation. The top of the aluminum can may not even be visible. And this creates a need for all sorts of clever techniques and a tremendous need for data. Then also tying into this is the irregularity of the items. So, the same category might be a milk jug. It may also be a single serve plastic container. It may be something that's not used for food packaging. It may have different pigments and dyes in it. And so again, just a real challenge you can see here where, a white painted piece of cardboard considered the same thing as a brown piece of cardboard. Some of the funner mistakes that you also have to deal with are these different icons, different graphics that appear on things. So you start to see the system making spurious correlations that can be hard to disentangle. So things like, having a symbol maybe it's a logo or something like that is the same across different material types, and the machine learning system using that as a visual cue. So, there's cows painted on a large number of different things. One of my favorites, although it was very frustrating to deal with, was identifying milk cartons. And there was a Costco box that had the cartons painted on the outside. So, it's seeing the carton and it's seeing the painting of the carton. Very hard to distinguish the two, at least from this overhead view. Nonetheless, using different techniques, using a tremendous amount of data, we've been solving these. And really, building a process around all of this. So, we're doing what I think anybody would expect for a supervised learning problem: collecting data, annotating it, deploying the systems, auditing the performance, and then using that to improve. But more and more energy goes towards what the team calls Operation Vacation, but the idea that the system should be able to improve itself with minimal human intervention. For us, the capture of data is easy. So we have a humongous amount of unlabeled data. Now that we have hundreds of systems all over the world, all pushing data back up to us, and there's no way to manually annotate all of it. So to the greater extent we have, we're using different semi-supervised techniques and other things. We're able to gain a lot of leverage over that information. So that's us. To summarize, we think we are part of the next generation of technology to change the recycling industry. It's an interesting problem, but it is a very solvable problem. And the recycling industry has its own quirks, but this creates all sorts of nice problems. Also, nice relaxations for machine learning. But yeah. Thank you very much. These are our robots deployed in SSR, single stream recyclers, sorting out paper, working, this very moment to clean up that paper and move the recovery rate of the country higher. I'm happy to take any questions. Oh, wait. Oh, I'm sorry. I guess I had another slide. And what does the road look like ahead? But as you'd expect with this amount of data collection, we are putting it everywhere. So we're monitoring more and more of the waste stream, and the industry is able to take advantage of that in different ways. At that point, thank you. Yeah.
Thank you. It was really, really interesting. We do have quite a few questions, not that much time, but so I'll start with the first one. We have an audience member that says that in some countries, the residential waste is single stream. Is that a feasible possibility for the US?
So I'll just be really pedantic. So in the United States, we call the recycling bins we have outside single stream, but that's still separated from the main garbage, and that's because there used to be multiple streams. Like paper was one place, and plastic was one place, and glass was another. So we are used in single stream. If you use that definition, if you mean actually going through the true garbage and trying to extract stuff, then absolutely. For the robots, it's not that different. Everything's a little bit more nasty.
Yeah, exactly. But, you'd have contamination.
But you have way more contamination. But at the end of the day, deep learning-based solutions can be quite robust to that type of contamination, and it's less of a problem even than a lot of the occlusion we've already had to deal with. There are then different issues if basically if your paper gets wet, you can't really clean it, and so it's less valuable. So you see these facilities be less viable, but from our technology's perspective, we can actually handle it just fine. Well, there are different performance caveats, but we can handle it.
And a question that I had, when you were talking about different numbers, plastic numbers, so do you actually detect like the characteristics, like the intrinsic features of like number 3, number 4, number 5 plastic, or do you detect the numbers?
That's a really good question. So we don't actually detect anything intrinsic about the plastic itself. If you take all the labels off of it and you flattened it out and you took away sort of visual cues for the form factor, our system would be fooled. But so would a person. The interesting thing about the recycling industry is you almost never have that situation. You have labeling on it, you have bottle cap colors, you have all of these visual hints as to what it is. So for number 1 plastics, which is like Pepsi and Gatorade bottles and things like this, we don't know that that's a number 1. What we know is this is a 16-ounce bottle that has a Pepsi logo on it, and we happen to know all 16-ounce bottles with Pepsi logos are number 1 plastics, PET. So we're actually doing sort of this inference, like sort of both inference in the machine learning, but like sort of inference about what the material is. And that's actually what people do as well when they're manually sorting it.
They don't like look for the number 2 low with the.
Yeah, so we can't go off of barcodes or the numbers because most of the time they're occluded. Yep.
And what happens? You mentioned that sometimes it's possible to recuperate and reuse some of the plastics, for example, with industry partners, I guess. So and that wouldn't be using barcodes either. That would be like actually detecting that this is a Nespresso pod.
Yes. Yeah, and this is one thing that gets us very excited is that by being this specific about what we can identify, so not just number 1 plastic, but yeah, this is Nespresso or something, it enables, well, it makes it so more materials can be viable to recover, and it can also enable new models for reuse rather than recycling. So if you say right now, if you were to say, hey, I can actually I can put your food in a container and that'll go into the recycling stream and it could come out intact and you could actually recover it and reuse it. That doesn't work because the industry doesn't have any ways to separate out industrial volumes of that stuff.
Yeah.
But robots can separate that out in industrial volumes and make these new models viable.
And I guess currently you mentioned that you use purely supervised learning. So essentially you would need to take a bunch of pictures of whatever canister or in order to add that new category, right?
Yes. Yeah. And that's, we've really engineered the whole system around that. So if there's something new we want to identify, we don't just take pictures ourselves, but we look out into the fleet and out of all the 100 systems, we start gathering data for that material. So we get it from
and labeling it.
And labeling it. And so we have all these different environmental conditions, different examples where branding may be different in different continents. And it gives us this vast data set to use. But yeah, it is primarily supervised. We have a large team of annotators that are constantly, improving or adding new categories.
And have you thought about different approaches, paradigms of, for example, reinforcement learning or semi-supervised?
Yeah, there's a number of different ways. So first, yes, we're pretty much always, combing the literature, looking for different, active learning techniques, semi-supervised techniques, to cut down on the need for manual annotation, or where manual annotation is used, focus on the areas where it'll have the maximal impact. There is sort of a fun, different domain, which is, so we don't use reinforcement learning today, but there are different opportunities to use reinforcement learning in things like the grasping of the robots. And that's actually, there's a lot of opportunity still available in the industry to improve performance using reinforcement learning for those types of applications completely outside the visual domain. So there's sort of like a whole rabbit, and there's rabbit holes of stuff we can get into. And, for us, the recycling industry is rich with these sort of things we can do, and we're only limited by, what we have to prioritize and limited bandwidth.
For sure. We have I think one maybe final question from the audience. Do you think your solution could drive a redesign of recycling facilities, for example, an agitator on the belt to cause item reorientation?
Yes, absolutely. We designed our system so we could fit into the existing infrastructure with almost no changes, because we saw that as the path to rapid market adoption. Now that the industry is more comfortable with our technology, we are seeing that facilities are getting built with robots in mind. So that does mean different ways the stuff is agitated, different layouts, even looking at different things like lines that would have been manually staffed. If you don't need any staff there, then you can remove a lot of support structures and things like that add cost to these facilities. So there's actually multiple layers of improvement that you can get as you start to look at building the facilities around both robots and AI-based vision systems.
But I guess you try to cover both use cases, both like kind of retrofitting and being more proactive about it.
Yeah, so our use cases around for a retrofit, hey, we can do the work of roughly 2 people. We can hit these purity standards. Here's how much it'll cost to kind of bolt this thing in. If you build this in from the beginning, we can actually go even further. You can get even higher throughputs if you do the layout better. You can hit higher purities and higher recovery rates if everything's distributed better. So like some sort of agitation. So a shaker table, like that's an actual device that like shakes material evenly. Yeah. If you have that, then you just get more and more out of the robots and higher leverage over pretty much all the equipment in the facility.
So you start from like the worst case scenario, like that you don't have access to anything special, and then you kind of go forward on that?
Well, and that's key because here in the US, you might be looking at a dozen facilities that get built each year.
Mm.
And that's actually not that big of a market. So the whole potential, if you convince everybody to put every robot in, you might be looking at 80 robots a year. Instead, if you look at the install base of all existing facilities, there's about 1,000 of them. And you'd say, okay, now you can start to really make a difference and deploy lots of different robots out there. So yeah, very much, we really ended up starting with the hardest problem and are now that we're accepted, we get to have easier and easier problems.
That's always a good sign. It means you're doing something right.
Yep. Hopefully, yeah.
Thank you once again for your presentation. This was really, really enlightening and inspiring, and you do amazing work. Thank you for being here.
No, we appreciate the highlight.
So this was the last session for today, everyone. Tune in again tomorrow. We have more presentations and another panel. And hopefully you'll get more inspired to use tech to fight climate change. Thank you.